This is just a long air core coil question, and you can look at my video about what long air core coils are in magnetic circuits and why they're used. They're used sort of to make inductors and transformers that are for very high frequency applications, often used in audiovisual equipment. Here you are going to calculate the current that has to flow. So I equals question mark to produce a flux. Our flux is known, 1 times 10 to the negative 5 Weber of magnetic flux, and it has N equals 1200 turns, which is not an official SI unit, but it's very handy to write it down as if it were one. And it has a plastic core that has a cross-sectional area of 6 by 24 millimeters squared, and it has a mean path length of 15 centimeters. So I reworded all of this. I see that this is a length times a width, so I did the cross-sectional area, and I reworded 15 centimeters long into mean path length because I know that that's what it represents. If I were to draw this, it would look something like this. It's sort of a rectangular cross-section, and it's very long. Now, it's very uncommon for there to be a rectangular cross-section on a long air core coil because usually you see sort of like hollow pieces of plastic that are wrapped. But here you have 1200 turns wrapped around a rectangular core for some reason. Now, you have to find the current I. So I'll just show you the approach to this question. What we know we know that this is a situation where the length is greater than 10 times the critical length or the diameter. Um, I'll just say width. So it's not a diameter in this case because it's a length times width. And we know, so because that's the case, we know that this will observe the following behavior. We know that it observes a behavior that the reluctance is equal to mean path length over permeability of free space times cross-sectional area. So that is a fact about long air core coils. And we always know that the force, the magnetic force that is making this flux get developed is equal to the flux times that same reluctance. So these are the two kind of relationships that you're working with here. So if I'm trying to solve for I, then where do I find that in here? Well, also commonly in magnetics, we have to remember that a magnetic circuit is a lot like an electric circuit. So in electricity, we have V equals IR, and in magnetics, we typically have F or FM equals flux times reluctance. And that is equal to the number of turns, or sorry, the current times the number of turns. So very, very common equation here in magnetic circuits is current times number of turns. And we do have the number of turns here, and we are looking for the current. So let's take our FM. This is the same FM, can also be related to N times I. So now I have FM equals N times I. I want to solve for I. So in this problem, I would just solve for I, Fm over N. At this point, I know N. Do I know Fm? Well, Fm, I see here, is equal to my flux times my reluctance. Now, I know flux because it's given here, and I know N because it's given here. What is my Rm? Well, my reluctance is here. So I can just substitute that equation in, that purple equation. So let's do that. Let's substitute that purple equation in, which is L over permeability of free space times cross-sectional area. And everything else in my equation already goes along for the ride. That was my flux, which I know, and my N was at the bottom as well there. So there we go. Now I do know L. I do know permeability of free space. Permeability of free space is always 4 pi times 10 to the negative 7. So we should definitely always know that. If we don't know that, we are going to have to be studying that. That's Henry's per meter. Let's see. We know the cross-sectional area is 6 times 24, and we know N, which is 1200. So at this point, I could just substitute everything in. That will make sure that your units all follow along. Everything crosses out. You should get amps. And that's how I would solve this problem that is a long air core coil in magnetic circuits.